In this tutorial, we're going to consider the polar form of a complex number. And let's still start from our basic general form of a complex number, which is a plus ib. So we are still using this as a general form, and we have represented that our z, the general form of this complex number z, is a plus ib. So which means that our a is our real part, while this represents our imaginary part. Now from this Cartesian diagram, or let me say from this graph, basic graph that we have, let's introduce the values. Now this is our y positive, these are y negative, these are our x positive, while this is our x negative. Now, since we have taken that into consideration, I told you that the real part corresponds with the what? X-axis, while the imaginary part corresponds with the what? Y-axis. So it means that point A here, let's assume that A and B are positive values, which means they are falling in the first quadrant. So it means our point A is going to be on the x-axis, that is, this is point A, while our point B is going to be on the y-axis, that this is what? Point B. Now don't forget, this is the origin O, and you know that the origin O starts from 0, 0. So it means that at this point A, this is at point A, 0, and this is at point 0, B. Using your Cartesian coordinate, that is, at this point your x coordinate is 0, while your y coordinate is what? B. At this point your x coordinate is A, while your y coordinate is what? 0. Now if the origin is at point 0 and this point is at point A, it means that the distance from here, from the origin to A, will give us A minus 0. That is, the distance between here is going to be A. So if I use a dimension sign to illustrate that, same concept. If here is at the 0 coordinate, or let me say the 0 point, now, and here is at the B point, it means that this vertical line, the length, is going to give us B minus 0. Our 0 here is our y1, our B here is our y2. So the difference between here and here will give us y2 minus y1, so which is B minus 0. So this will give us B, that is from here down to this point. So since we have derived this to be our A and this to be our B, we know that this is going to be at a 90-degree angle. This is A. Our theta, now there's another thing we need to define. Our theta is always measured from OX. Theta is always measured from OX, or let me say OX positive. So this is our O, this is our X positive. You always measure your theta from this OX axis. So it means that if we have to draw a line to measure theta, starting from the OX axis, we draw that angle till it gets to what? Till it gets to the complex number. So it means that this is going to be what? Our theta. So now, getting into derivations, we are now considering this number, or let me say we are considering this diagram. First thing, we have some derivations that we can derive using SOHCAHTOA. Don't forget, the goal here is that we want to find a general form for the polar form of a complex number. Now from SOHCAHTOA, we know that sine theta is equal to what? Opposite over what? Hypotenuse. We know that cos theta is equal to what? Adjacent over what? Hypotenuse. We know that tan theta is equal to what? Opposite over what? Adjacent. Now, since sine theta is opposite over hypotenuse, it means that sine theta will give us our opposite from this diagram. The side facing the theta angle is our side B. So this will give us what? B over our hypotenuse. Our hypotenuse is what? Our hypotenuse, that is z. So now, is since our hypotenuse is z, now let me I want to represent this z, because when we are talking about the general form, z, I've initially represented z as the length of the complex number. So but let's use another letter to denote it, and that is letter r, because z is more like the representation of the complex number. So let's assume that we are using letter r. So instead of having this z, I'm now denoting the length of this complex number using what? Using r, that small letter r. So it means that our hypotenuse here, instead of using the z, I'll now use what? R, where our z is equal to our r. So it means sine theta here is going to give us b over hypotenuse, which will give us b over what? B over r. If you cross multiply, b will be equal to r sine theta. That's our first equation. Now also from here, cos theta is adjacent over hypotenuse. Our adjacent here is what? A over our hypotenuse. Our hypotenuse is still what? R. If you cross multiply, it means that our A is equal to what? R. Our A is equal to R cos what? Cos theta. Now for the last one, tan theta is going to give us, our opposite is what? B. Our adjacent is what? A. So it means that our tan theta is equal to b over a. That is, our theta will give us arc tan b over a. Now taking a look at these derivations, since we have derived b to be r sine theta and a to be r cos theta, and I've given you that the length, our z, which is equal to our r there, using Pythagoras theorem. Pythagoras theorem states that hypotenuse square will be equal to opposite square plus what? Adjacent square. So our hypotenuse here is r. R raised to power 2 is going to give us our opposite square. Our opposite square, that's b square, plus our adjacent square, which is what? A square. Now r square will give us b square plus a square is the same thing as a square plus b square, because addition is commutative. So we can write this as a square plus what? B square. Now we have derived that r square is equal to a square plus b square, where r is the length of the complex number and z is the complex number itself, while r is now the what? Length of the complex number. So we have gotten that the length of the complex number is equal to what? A square plus b square. That is, if you simplify further, your r will give you square root of a square plus what? B square. Now z is the complex number itself. It means that z, the representation for all complex number, is what? A plus what? IB. So it means that the polar form of representing complex number, you're not going to express your real part in terms of what? The length of the complex number and the angle of inclination from the positive y-axis. So it means that the z will now give us, instead of writing a, I'll now substitute what? R cos theta. Instead of substituting b, I'll now substitute what? R sine what? Theta. So this will be IR sine theta. So from here we can factorize z, we can factorize r out. If we factorize r out of this, this will remain cos theta plus what? I sine theta. So the general polar form of a complex number a plus ib, the polar form is what? R cos theta, r into cos theta plus what? I sine theta. Now this theta that we are talking about, this theta, the same theta that is arctan b over a special name that we can attribute to theta is that theta is called the argument of the complex number. Let me write that out. Theta is called the argument of the complex number. So theta is called the argument of the complex number. That is, we can say that theta is equal to the argument of what? Of z. So, and it is important for you to still note when you are finding your arguments, you don't use the positive or the negative sign of A and B. What do we mean by that? If you are finding your argument here, your theta here, arctan B over A. For example, if you have 3 plus I2, it means that your theta here is going to give you arctan uh, B over A, that's 2 over 3. Now, the reason why we're substituting this directly is because I'm well aware that 2 and 3 is going to fall in the first quadrant. So it means that we don't need to find, it's not necessary that we draw the Gann diagram for this to know what we are going to substitute. So that, of course, this is still what we are going to substitute, but if the anger diagram falls in a different quadrant, for example, if your anger diagram falls in the second quadrant, it means that you can label that angle as E, for example. That is, your E is equal to arctan something. Then to now get your theta, that will be 180 minus E. This has been discussed in the last tutorial when we sketched the anger diagrams for each of those complex numbers. So we are actually going to do an example now. We are to express z is equal to 2 plus I3 in polar form. Right, to express z is equal to 2 plus I3 in polar form. So of course, you need to sketch your Gann diagram first. Sketching the Gann diagram for this. So let's have our y-axis first, followed by our x-axis. So these are y positive, these are y negative, these are x positive, these are x negative. Now, what is going to correspond to our x-axis here is 2. What is going to correspond to our y-axis here is what? Plus 3. So plus 2 on the x-axis should be around this point. Plus 3 on the y-axis should what? Be around this point, using it as a sketch. So if we join a point to connect the intersecting where we are going to have points 2, 3, we should have something like this. So drawing the length of the complex number down to the origin, this will be our what? This will be our R. Now don't forget, this is our 90 degree. From here to here is what? 3. From here to here is what? 2. So it means that from the formula that we have derived already, that R square is equal to A square plus B square. Our R square here is going to give us 2 square plus 3 square. It means our R square will give us 4 plus 9. This means that our R square will give us 13. This means our R will give us square root of what? 13. And square root of 13 should be around 3.606 using your calculator. So now we have gotten the length of the complex number. We need to find the arguments. Now, since from the positive OX plus axis, if you draw your curved line, this is automatically going to be your theta. So you don't need to subtract it from any of the 180, 270, 360 numbers that we have been proving initially. So here, directly, tan theta is going to give us what? B over A, where theta is the argument of the complex number. It means that tan theta is equal to, our B is what? 3. Our A is what? 2. So tan theta is going to give us 1.5. That is, our theta will give us what? Arctan 1.5. So arctan 1.5 is going to give us, using your calculator, that's going to give us 56.3099. So, and if you leave it in degree minutes, that will be 56 degree 18 minutes. So our theta is 56 degree 18 minutes. Now don't forget, The general form of a complex number is z is equal to a plus ib. The polar form for a complex number is represented as r cos theta plus ir sine theta. So which is the same thing as r into cos theta plus I sine theta. So here z is going to give us, our r here is what? Root 13, which is equivalent to 3.606 into cos. Our theta here is what? 56 degree 18 minutes plus I sine 56 degree 18 minutes. So that will be the correct answer to this particular question. The polar form of a complex number, we have derived that as what? Z is equal to r into cos theta plus I sine theta. Now, the shorthand form is represented as z is equal to r, then we have this symbol, then you have your theta, like an upside division. So this is the shorthand form in which you can use to represent this. Z is equal to r into cos theta plus I sine theta has the same meaning as this. So it means that in the earlier question that we got our z to be equal to 5.385 into cos 158 degree 12 minutes plus I sine 158 degree 12 minutes. Okay, I don't think this is what we got in the previous. I think this is another, I'm assuming another value. So here, if we are to represent this in the shorthand form, our z will give us, this is still our r, 5.385. Then we are now going to have our angle 158 degree 12 minutes. So this and this means the same thing. So for this tutorial, this is where we're going to end on the polar form of a complex number. See you in the next tutorial.